Hey, you're good. Okay. Going well. I had a quick question. So the random quizzes, surprise quizzes, those will happen during lecture, right? So will I, if I join the live stream, would I be able to still do that? Oh,
Yeah, so like in general, like I just try not to push the live streams like that hard in the beginning of the semester so that people don't get used to it. But the answer is yes.
okay, great. Thank you.
Yeah.
Appreciate it.
Do you guys have lecture before?
Some people have.
Yeah, because I think we're making lecture.
I can't imagine.
Yeah. Like you got yeah, yeah. Yeah, I think that's the countless people coming in.
Not to criticize or anything, but when I was late to class last time, I made a show of being in a hurry. So take a seat. All right, so while the people in the back, so I think the derivative of the people coming from calculus is approaching 0, so that's good. Calculus is very useful in everyday life. Don't let anyone tell you otherwise. So while people are finding their seats, the first lab is gonna happen this week. So for some people, it's gonna be Wednesday afternoon. For some people, it's gonna be Thursday afternoon. So if your lab is on Wednesday, just go to SF 1012, 1013. Find a seat. If you can find a partner ahead of time, that's great. If not, we'll find a partner for you. So those lovely people are going to be there. So they're going to introduce themselves before. So they're there to help you along as you do the lab. The lab handout is going to be posted sometime before Wednesday noon. It has to be like that in the beginning of the semester because I don't exactly know how far I'll get in the lecture. And, you know, like 20% of one lecture makes a difference. So later on in the semester, if I'm posting it like just a few minutes ahead of time, that's just because I'm late. The calendar has been updated. I need to click OK. So the calendar has been updated. So you have your learning outcomes over here. There's learning outcomes over here that you can expect to have. If you need to talk, please text. Okay. So that's going to be like that. And again, kind of as we progress towards the semester, things are going to be more predictable. Of course, like, you know, like we are like 10 minutes behind and some of those learning outcomes might not happen, or we might be 10 minutes ahead and there's going to be more. So you get those for free. There's suggested readings. There's slides here. So the lectures are being live streamed on YouTube. So that's on my channel. Like and subscribe. And they're also linked here. Unfortunately, the lecture 1 stream is just my mug. I neglected to share my screen. The lecture 2 stream is all good. and the lecture 3 is being streamed right now. Hopefully it's good. With that said, like the live streams are there if you are sick, but in general, I encourage you to come to lecture. There's people coughing, you'll get sick eventually as well. But if you don't, please come to lecture. It's probably better that way. Okay, all right. So I want to talk in a little bit more structured way about floats and integers, and then we'll move on to a different topic, functions. So like we mentioned, so integers can have an arbitrary number of digits. Of course, at some point you'll run out of memory, but outside of that, an integer can be any number. Floats contain a fixed number of digits. So they're basically stored in scientific notation in binary. We're not talking about binary representation right now. We're just talking a little bit abstractly about, well, there's a fixed number of digits. How many digits? Well, it actually depends on the hardware. Different computers, different phones, whatever, are going to be different. Have a seat, please. Welcome. So there's like some free seats over here. There's like a lot over there. Lots to choose from. Okay. So how many digits? On most machines, it would be 52 binary digits for the A. So for the coefficient, and then it's going to be 11 for the exponent. That corresponds to about 15 decimal digits that you can store in a floating point number in the mantissa, so the base. And 11, so approximately 3 decimal digits in the exponent. So more details about how that actually works in the hardware are coming up. For now, I just want to experiment a little with Python in order to see what that means. So I can say, okay, I want to print a number like 3.14. So that will look the way you would expect it to. It would print 3.14. So in Python, I can also use scientific notation. So I can write something like 1E30, and that means 10 times, so 10 times 10 to the 30. So let's just make it 2 so that it's clear. This is 20 times 10 to the power of 30. Okay. Is the font big enough for the people in the back? Okay. So, all right. So I can execute that. And that will print, again, in scientific notation, 2E plus 30. So that means 2 times 10 to the power of 30. So what I mentioned here is that we have approximately 3 decimal digits in the exponent that we can store. So what that means is that if I say 2 to the power of 300, that's a very 2 times 10 to the power of 300. So that's a huge number, but that is something that we can store. On the other hand, if I try to print something like 2 to the power of 3000, that is just not going to work because, well, I said approximately 3 decimal digits. 3000 is 4 decimal digits, so can't do that. So what's going to happen is this is going to print, and this is going to print as inf, meaning, you know, like as far as Python is concerned, the floats that's too large is just infinity. So there can be weird situations because of that. So for example, I can say, well, like I want A to be 2 to the power of 3000, and I want B to be, again, I misspoke, 2 times 10 to the power of 3000. That's even larger. And I want B to be 2.5 times 10 to the power of 5000. And now I might query, what is the value of A is greater than B? So if you remember, every expression like that, and we'll come back to that later in the lecture today as well, is either true or it's false. So which is it? Do you think it's true? do you think it's false? Anyone? Yeah,
False.
it's false. Why is it false?
A is not greater than B.
That is one way for it to not be true. Yeah. So A is not greater than B. So in fact, that is true. So that's going to be false. And that's because that's because A is like 10 to the power 3000 and B is 10 to the power 5000. So A is definitely not greater than B. But on the other hand, if we also try to print B is greater than A, what is that going to be? So that was false. And so let's try this first. So is that going to be false? It's going to be true. Yeah. That's right. So here's what's going on. So we'll visualize the execution here. So here we have A is infinity and B is infinity. And the reason A was not greater than B is that A is infinity and B is infinity. So in the same way, B is infinity, A is infinity. So it's not the case that infinity is greater than infinity. They're both stored as just infinity. So that's going to be false as well. So that's a little bit weird. And we'll see issues like that come up when you're dealing with numbers that are very large or numbers that are very close to zero. So you can also have something like C is equal to 1e negative 300. So that is 10. So that is 10 to the power of. Sorry, this, by the way, was in the tube. So that is 10 to the power of negative 300 times 1. And that is a number that's very close to 0, right? So that is equal to 1 divided by 10 to the power of 300. So very, very small. And here, that you can still store. So here C is recorded as 10 to the power of negative 300. So that's fine. On the other hand, if you have D1E, minus 5,000, so that is 1 times 10 to the power of negative 5,000, which is the same as 1 divided by 10 to the power of 5,000. So here, D is just 0 now. Okay. Why is that? Well, because in order to store it, this would be like 0.00000 something. And you have a limited number of digits. So the 1 just doesn't fit at the end. So you have those kinds of phenomena that you can watch out for. Now I'll spend a few minutes talking about something that's maybe a little bit more advanced, but still maybe worth talking about. So we had this issue of cannot store a number that's too big, cannot store a number that's too small, because you have approximately 3 digits. So again, approximately 3 is a weird thing to say. It's exactly 11 binary digits, but we'll talk about what that means later. So approximately 3 means 300, you can do it. 400, you can't. So most numbers you cannot represent precisely, right? So even a rational number like 1/3, you cannot represent precisely using decimal notation. You cannot represent it precisely using binary notation either, right? So if you try to store 1 divided by 3 in Python, what's going to be stored is not exactly a third, but something like 0.3333, and then eventually you round to the next digit. Most numbers are irrational. So for example, pi is famously irrational. So that means that, you know, it has an infinite amount of digits, and it doesn't matter how many digits you try to represent pi as, there's going to be more, and it's going to be non-periodic, unlike 1/3, which is periodic. So again, if you want to represent pi, you're going to have kind of in the flow to store it approximately. So can it be another way? The answer is, well, kind of yes and kind of no. So for rational numbers, you can very well imagine doing it the way you were taught it in middle school, right? You were probably not taught decimal notation first. You were taught a fraction is like 2 divided by 3. And if you want to store a rational number, you totally can. You can just store 2 and 3 separately, and you'll store the number exactly as it is. You can run out of digits for integers if you run out of memory, but that's a theoretical concern. So you could do that, and people sometimes do that. But most real numbers are irrational, so they cannot be represented as this fraction n over m. Some of them you can store. So for example, the number pi, you might not have noticed, but on this very slide, the number pi is stored extremely precisely to infinite precision. That is not a joke. Like the pi over there, it means the irrational number pi to an infinite precision, right? So more generally, you can store a number like whatever, square root of 2 divided by pi to the power of e, like on the slide right there. That's already stored in the computer memory. It's right there, right? So you can store a sequence of symbols that represent some irrational numbers. However, most irrational numbers cannot be expressed as a fixed symbol that people know about or as an algebraic expression. There's just too many of them. So most of them you could not possibly mathematically store, nor do you need to, right? So usually it's faster to operate on a single value, and that's why people use floats rather than rational numbers for one thing. For another thing, if your numbers come from physics, come from the actual physical world, you do not need to store them with infinite precision. Because if the number came from a physical measurement, that measurement itself came with a certain precision, right? So if you think about whatever, like how long does it take for a ball that rolls at whatever 3.0 meters per second to traverse 10 meters, the answer is, well, like approximately 3.33 seconds, you would not want to write it down as 3.33333 because that's probably not true. Like you would be misrepresenting how precisely you know the answer because you probably don't know the velocity exactly and you don't know the 10 meters exactly either. And that's why in physics, usually they will tell you, don't write the final answer to a larger precision than what you can actually be held accountable for. So, okay. So that was kind of like a little bit of a philosophical issue. So here's a very practical thing that comes out of it with code that we've already written last time. So again, for those experiments, I think it was enough to see them. The functions I actually want, or the code right now, I actually want you to type it in, and I'll type it in again. So we'll do like whatever, like A is 1, and B is 2, and C is -9. And we'll do discriminant is B squared -4 times A times C. And we'll say if discriminant is greater than 0, then R1 is, again, giving you an opportunity to type it in. And I'm typing it in as well. Yes. Yes, thank you. Is that okay now? Thanks. Yeah, and thanks. You should, like, if you don't hear anything or don't see anything, please tell me, because otherwise I wouldn't know. So again, Shift End on a Mac to select until the end of the line. Command Shift Right. On a PC, Shift End on the Mac, Command Shift right, Command Shift left to select like this. And I'm now doing Control C, Control V. And I'm now changing this to a minus. I could do that very quickly. Hopefully you will be able to do it quickly soon enough as well. And I'll print R1 and I'll print R2. And if the discriminant is equal to 0, I'll compute. So what I'll do now is a little bit different from before, just for fun. So I'll just compute R1. So the discriminant is equal to 0. So this is just 0. And I'll print R1. And else I'll say no real roots. Sad face. So, okay. So that's going to be like this. So I made C be negative so that the discriminant is very positive. And here you have the two roots. So R1 and R2. So now kind of what's a root? Well, it's the number that if you plug it in back into the equation, it's going to be 0. So let's try doing that. So I'm going back and here I'm going to say print A times x squared plus B times x plus C. R1 rather. Right? So what you would expect if Python worked the same way as algebra would is that it would print what? 0. Yeah, because like the root is the number that if you plug it in, you'll get the 0 back. Let's see what actually happens. It actually did print 0. So I'll just change it a little bit so that it doesn't. I think I'll cheat a little bit and I'll compare it to 0 instead. Yeah, I actually like, so like sometimes it works, sometimes it doesn't. I'll just play around with the numbers a little bit until it does. That is true. Wow. I'm not lucky today. Yeah, so I actually wrote down numbers that worked, but it does not always work. Okay, told you. So why didn't it work? Well, because R1 is not stored exactly, right? So it's this expression with like minus b plus square root of discriminant divided by 2a. So discriminant to the power of 1/2 is some irrational number that's approximated with finite precision. So that means that R1 is not stored exactly, it's rounded off. And that means that you plug in R1 and it's the expression doesn't work out exactly to 0. So now that it displayed false, I can go back and print R1 as well. Actually, R1 was already visible there. Sorry, so not R1, but rather the expression. And just print last. And what you have is this very small number that's approximately 0, but not exactly. Yes.
Is there a specific number to which irrational number can rounding off to?
So it's rounded off to the nearest digit, right? So you have exactly 52 binary digits, which works out to which works out to about 15 decimal digits. So if you think about it as the decimal representation, it's going to be rounded off to like around the 16th digit of the number. All right.
And if it's a very large number, then it will show it in like exponent numbers. It would be like 1.1111.
So the way it works is it's always stored as kind of the first digit, binary point, and then the fractional part, and then times the exponent. So the point doesn't actually move, the exponent changes. Yes.
Like they gave it as infinity, but like there's single digits. So does that keep like even before the
No, so it's not that it didn't work, it's that if it was 10 to the power of greater than about 350, it just represented it as infinity because it cannot represent more than approximately 350 in the exponent. Here, we're talking more about what can be represented in the base. So we're talking about the A rather than the B here, right? So we're saying in the A, there cannot be more than 15 digits of precision. Okay, and B, there cannot be more than 3. So those are separate issues. Okay, good question. Yeah, other questions? All right. So, okay, I want to move to a new topic, and that's functions. So you already know some functions and some syntax for functions, even though maybe you hadn't thought of it that way exactly. So in algebra, if you write something like f of x is equal to x squared, what that means is you define the function that you named f. It has what's called an input parameter x. So x is what you plug into the function. That's what's called a parameter. And the function computes x squared. So the square of whatever you plugged in. So there is syntax there, right? So the parentheses are an arbitrary way of representing functions, right? So you're saying f of x, the parentheses are just notation. In the same way, the equal sign is just notation. It just says that the function computes whatever is on the right-hand side of the equal sign. Does that make sense? So in the same way, Python has a way of defining functions. So the way it works is the name of the function goes over here. In Python, unlike in algebra, the convention, although you don't have to, you can name a function f, but the convention is for the names to be word, like possibly one word or possibly multiple words. And part of it is that in algebra, like you would write it down by hand, so kind of conciseness is good. In Python, you type it out, so it's fine, and it's kind of more readable that way. So the parentheses work the same way as in algebra. Def means here comes a function. And then whatever comes after the return is whatever the function computes. Right? So this Python function square is just the same as the algebraic function f. Make sense? So we can write and test functions, and we'll do it in a second. From now on, we'll use this convention of separating out the function definitions and the use of the functions with this mysterious if name equals main line. So for now, just think of it as a separator between the function definitions and the use of the functions. Later on, we'll explain what it actually means. So I think you might imagine what this would print, but even so I'm copying this and pasting this into Python Tutor. I encourage you to do the same. So here what happened is we are about to say print square 6. And what's gonna happen is the 6 is gonna get sent here. So the 6 gets sent to the x. And then the function computes x squared. And that gets printed. Okay, so this should be pretty transparent to you if you just think about it as we define a function just the way we define a function in algebra. This is square of x is equal to x squared. And then we said, I want to compute square of 6. So what's square of 6? Well, it's 6 squared from over here. So that's why it prints 36. Does that make sense so far? Yes. So the answer is you do not need to do that. We're doing it for reasons that will become apparent later on. So I'll keep doing it because there is a reason, but I'm not going to explain right now. Yes.
So is that name equal to?
No, sorry. So just a convention for now. We'll explain exactly what it means in a few weeks. You do not need it. We're doing it by convention for now, and there's going to be a deeper reason for why we're doing it later on.
So it's just a form of selection to.
So like you're insisting on an answer and it's a long answer. The answer is this becomes relevant when you're having multiple files in the program. Right now, it's just a separator between the function definitions and the use. Yes. Yeah, there was a question over there. Yeah. No, so what you see as you see it worked, right? There are ways of doing it in Python. You do not have to, and we are going with this for now. Yes. Yeah, that's a great question. The answer is yes, totally. So just like in algebra, you can say, I'll do you one further and I'll do like square. So 36, let's add 4 so that it's a nice and round number. And if we score, yeah, so, okay. So that would be 1600 because 36 plus 4 squared is 1600. A great question. We'll come back to composing functions later. Okay, other questions? All right. So functions can have multiple parameters. So for example, I could have a function named add that computes x plus y plus z. And the way I use it, so we say call the function add, is I say add 4, 5, 6. So the 4 gets sent to x, the 5 gets sent to y, the 6 gets sent to z. And then what the function computes is the sum of the 3 numbers that you send to it. Okay, so you'll see kind of multivariate functions in calculus imminently. You might learn how many people have seen kind of a multivariate function in high school? So not everyone, but yeah, you don't worry, you'll see those soon. So functions can have what you might say is kind of scratch work. So this is now a little bit different from what you would see in algebra. So what's going on here? So what I'm saying is it's the same function. It's still doing addition. But what I'm doing now is I'm saying, I'll just say, well, like, I'll keep track of this variable s that initially is going to be x, and then I'll change it to s plus y, and then I'll change it to s plus z. So let's run this and see how that works out. So we are over here. So we're saying add 4, 5, 6. So I press next. And what happens is the 4 got sent to x, and the 5 got sent to y, and the 6 got sent to z. Right? And now I'm saying s is equal to x. So take x, put it into s. So S is now 4. And now I'm saying, never mind, I want S to be the old S plus Y. So the old S is 4, the Y is 5, so S is about to become 9. And now I'm saying the old S plus Z, so S is now 15. And of course, like, like you put X into S, and then you add in Y, and then you add in Z, what you get is X plus Y plus Z. Right? So that's a little bit different from what you usually see in algebra, because really what's happening is there are multiple lines there getting executed one by one, and then what gets returned eventually, so what the function computes eventually, is whatever comes after the return, which can involve doing kind of scratch work. Does that make sense? Yeah.
Is there a way instead of writing x equals s plus y?
There is, but not gonna do it. Plus equals, yes. Yeah, over there. Yeah. So that's a good question. The reason you might like to do it is because it's difficult to write everything in a single line. Sometimes it might be impossible. So this is obviously for the sake of the example. In fact, you didn't need a function. You could just write x plus y plus z directly. So it's going to become more apparent later on as we write more complex functions. Yes. Say again? That's a good, so the answer is no. We'll see that in a second or possibly in 2 days, depending on how things go. Okay, other questions? All right. So what I want you to do now is to actually write something yourself. So that's going to be very simple if you followed along for now. But again, like really important to get your hands dirty because otherwise kind of nothing works. So please write a function that basically computes R1. So I want for this function to actually compute R1. So this is incomplete right now. And I want for this call to actually have concrete A and B and C so that you can see that the function actually prints the right thing. So I'll give you a few minutes. So what I suggest you do is copy and paste this template into Python Tutor and get to work. Talk to your neighbor if you like about Python. Man, those derivatives, right? And all right, so let's take kind of maybe 3 minutes.
All right, how many people are still working on this? All right, you want like a representative question? So kind of to be clear, one group, just her ones, don't worry about the discriminants. I mean, if you were worrying, that's great as well, but you don't. Okay, so let's.
Yeah, no, I did not tell that about that. We did not do that. Like, that you want. I did not. No, that's I don't know if it was.
Okay, all right.
So what do we do? So we can say, you know, our one is again minus b plus. I'll do the discriminant. And again, this was to your question of like, why do scratch work? Well, technically you could put it all in one bit formula, but that would be kind of a cumbersome formula, right? So it's kind of more convenient to write it this way. And I'll divide by 2 times 8. Say it? Yeah. And then here, so I'll set up an equation such that it will have a root. So x minus 1 squared, for example, is x squared minus 2x plus 1. And it has the root 1. So I'll just say 1 minus 2 and 1. And now I'll run it. My code is running. Wait up to 10 seconds. I think the 10 seconds are over. Oh, okay. Yeah, we're done. Okay. So what happens? Sorry, quiet down, please. Quiet down more. Thank you. I know it's like 3 minutes, well, 5 minutes before 6, but still. So, oh, I didn't say return. That's a good point. I meant to say return R1. Oh, now I have to wait another 10 seconds. That's great. So, okay. So 1 got sent to A and minus 2 got sent to B and 1 got sent to C. We can see it over here. And now the discriminant has been computed. So the discriminant is 0. And now we've computed R1. So R1 is 1.0. And now the value of this is going to become 1.0. And now that's going to be printed. Okay, quiet down, please. Nothing so important that it cannot wait for another 3 minutes. Except this lecture. So, okay. So, all right. So, an important thing to know is that, like you asked before, like, does the scratch work exist outside the function? The answer is no, it doesn't, right? So if I do something like add 4, 5, 6, and then I say, hey, like, what's x? The answer is, well, x doesn't make sense outside the context of the function add. In the same way, what s is really doesn't make sense outside the function add, because it was just defined as scratch work for that particular input. Yes.
So they can do variable call.
Yes, you can. Yeah. Yes. So we'll do that kind of in more detail later on. So that works the same way as what you would expect from algebra, right? So imagine that you have like f of x is x squared and g of x is x cubed, and you compute like f of 5 and also g of 8. And then like the question like what is x does not make sense, right? Well, like it was a local variable. You plugged in 5 and you also plugged in 8. Depending on the context, it was something different. So that works the same way in Python. If you try to query the value of x, you'll just get an error. Okay, so there's like one more exercise. So that's supposed to give you a hint for the task on the next slide. So one thing to note about this meme is that we now know that this should be 2 equal signs, not 1, right? So x equals 7 in Python is an assignment. It's not true or false. So it should be like x equals 7 if you're talking about Python. We don't really have time for this. So I'll leave this for you and we'll come back to it on Wednesday. Please write the expression such that this will be true when it should be true and false when it should be false. All right, I will see you in the lab if you have a lab on Wednesday. Otherwise, I'll see you in lecture. Bye. Thank you.